So he said everything, so I'm just going to start the demo. And since we are demoing a debugger, we need, a guinea pig program to debug. And I wrote one, and I'm keeping it over here. So this is a really simple program, so I'm not actually going to show you the source code because you would read it and figure out what the bug is immediately. So I'm just going to show you how to compile it. And over here, it's the executable. And if we run the executable, so most of the times it works. But believe me, if we sat here and ran it long enough, we would actually get a seg fault eventually. Unfortunately, today we are not blessed with a seg fault, but that's not a problem. I was planning for it, and I also wrote a test that does some things and crashes reliably. And there we go. So, by the way, if you are trying to debug a program in a real program, a bug in a real program, I suggest that you do something like this. You first write a test that reproduces the bug somewhat reliably and without interaction, and then you debug the test. Of course, you cannot do it that every time, but if you can, that's the best way to use a debugger. Okay, now I'm going to show you how to debug this test. The command to run the test is this, and to run the debugger, you just replace Go with Gdlv and run it. And this is the main window. I'll give you a short tour of the main window of Gdlv. At the top left, it's the listing window, which will contain the source code that's currently being run by the program. Now, I know that now it's showing a disassembly, a scary disassembly, but that's because we are debugging a test, and tests in Go do not have a main function. Of course, you don't write a main function. It gets generated automatically by the compiler, so there is no source code for the main function, and that's why it's like that at the moment. But I promise you that shortly you will see source code over there. At the top right, you have the stack window, which shows you the current stack trace. You can see that there are 3 frames. The top frame is main.main, and then you have runtime.main, which is the runtime function that is responsible for calling init functions and then calling your main.main. And then we don't care about runtime.goexit. And if you go over to this window and click on a different frame, what will happen is that the listing window will change to show you the code that's running on that frame. So if we do that, and over here, that's the code of runtime.main. And the window at the bottom right, it's the variables window, which shows you the value of the local variables of the function that's either being executed currently or on the currently selected frame. So for example, over here we have 2 variables. We have G, which I won't tell you what that is, but you can look inside it. And then you also have a need unlock variable, which is just a Boolean with the value false. Now, the reason the third variable is not readable, that's because the runtime is always optimized, and sometimes in optimized code you can't see all of the variables. So that doesn't matter. Finally, bottom left window, this is the command window, and most of it contains output either from Gdlv directly or from the target program that you are debugging, if it happens to write to standard output or standard error. And at the bottom here, this text box over here, that's the command, that's where you enter commands that, then the debugger will execute. So let's get back to our guinea pig program. We had a seg fault, so let's reproduce the seg fault inside the debugger and see what's going on. To do that, we use the continue command, which we can also shorten to simply just C, and we press enter. What this will do is it will continue until either the program ends its execution, it hits a breakpoints, or it hits an unrecovered panic. And presumably what will happen now is that it will hit an unrecovered panic. So here we go. That's our panic. And the stack trace window filled up with a bunch of frames. And if we look through it, we can see that there is a bunch of runtime frames that are concerned with processing a panic. And over here, that's the offending frame. And we can see that we called a function, and it returned 2 values. And then we tried to dereference one of the values, the Q variable. And if you look inside the variables window, you can see the Q happens to be a pointer that is nil. So that's why it crashed. And now we would have to figure out why a complex function sometimes returns nil as the second return value. So I'm going to show you a couple of ways, actually 3 ways to do it. So the first one is the naive way, which is we go over here, we set a breakpoint on this function, then we restart the tests, which you can do by simply pressing R. Restarts the test, and then we continue. And now that we are here, we can step through this code. And to step through this code, we have a few commands. The first one is next, or simply n, which steps over one line of code, executing any function call that that line of code may do. And we also have the step command, which does a similar thing to next, but actually steps into any calls that the current line line of code happens to do. Like this, you can shorten it to simply S. And finally, you have the step out command, which exits from the currently executing function, and you can also abbreviate it to simply O. And there we go. Now, this is a bad way to do this, because as you can see over here, both return values of a complex function happen to not be nil on this iteration, so you would have to iterate potentially up to 100 times in this case, which is a very boring thing to do, and I do not recommend it. So let's see another way to do it. Now, let's continue until it crashes again. Let's go back all the way to our offending frame. And as we can see, this happens when the value of I equals 47. You can see that over there in the variables window. So what we will do is we will set a breakpoint here, and then we edit the breakpoint and set as a condition I equals 47. There we go. Now we already crashed, so we have to restart the tests once again and then continue. We stopped over there, so we continue once again. And now, as you can see, we are on this 47 iterations. And if we stepped inside a complex function and stepped all the way through this function over here, we would figure out how it actually happens to return nil on this iteration. So this is the first way that you could do this. And now I'm going to show you a second way. To do that, we are going to exit from the debugger, and we are going to use a program that's called RR, Mozilla RR, which is an open source program developed by Mozilla, which is essentially a debugger backend that can record the execution of a program and then play it back either forward or backward. And normally, if you use RR by itself, it will start GDB as its front end, but we have an integration with RR both in Gdlv and in Delv, so you can use RR from inside Delv or Gdlv, and it will look like just debugging directly, but you will also have the opportunity to rewind the execution of the program. So to do that, what we do is we take this command line and we add RR semicolon to say record the program, record the tests in this case. So we execute this, and it's recorded the tests. You can see that in the output window that you have already the crash over here because it recorded and executed it, and now it's rewound the execution, and we are back on main.main. And what we can do is we can continue again. Let's actually remove both these breakpoints. So it crashes again. And now that it crashed again, we can go back to this frame. We can set a simple breakpoint over here, no condition. And now what we do, we will use the rewind command. Okay, I need to actually select the input, which can also abbreviate to RW. And now, since we are at the end of the program, after it crashed, and if we rewind, what rewind does is executes the program backwards until it either hits a breakpoint or gets all the way back to the start of the program. And since the last time the program executed that line was the time when it crashed, we will get there, and I should be equal 47. So rewind, and we are there, and I is equals 47. And that's another way to do it. So there are a couple of problems with RR, and so it's fine, but it needs a couple of preconditions. You need to have to be using Linux, and you need to have an Intel CPU and a recent kernel. Otherwise, it won't work because, well, the magic fairy dust that they're using doesn't work unless you have those things. So, toy programs are fun, and but actual real programs are more fun. So, for the second part of the talk, I'm going to show you debugging a real program. And I decided to pick a program that we have probably used, everyone in this room has probably used. We are going to take a look inside the compiler, the Go compiler. To do that, the first thing we need to figure out how to compile the compiler. And it's really simple. You just have to go into this directory where the compiler lives, and you type go build. And it's built the compiler. It's this compile binary over here. Now, there is a difference between the compiler of Go and Go build. Go build happens to be a tool that's more like make, if you have used a C, for example. And what it will do is it will call the compiler a bunch of times for every package that you have, and then it will call the linker and put everything together into an executable. And we are not going to look to that. I think the compiler is fine for now. It's complicated enough. And so we're just going to look to the compiler. And to execute the compiler, you type compile, and then you give it a source code, a Go source file. For example, we're going to give it this source file. And I'm also going to add an option over here. That's this is not necessary, but I'm going to specify e = 4 so that it compiles concurrently. It doesn't matter for this, but it's for something later. And if you run it and you look at the directory, you can see that it created a .o file, which is an object file, which then you would have to pass to the linker to get an executable. So let's look at the compiler. To look at the compiler now, you can see that before we said Gdlv test to run tests, but this isn't a test. We are debugging a program with an actual main function. So to do that, we will change test to debug. And then after the debug verb, we can specify any argument that you want to pass to the underlying program that you are trying to debug. So in this case, we are going to pass -c = 4 and then the source file. I'm going to make another edit to this line. I'm going to go over here, and I'm going to add RR semicolon, so that we are going to record the execution of the compiler and play it back. So if I make a mistake and go too far, I can go back to the current place. Also, I'm going to show you that Mozilla RR doesn't just work on 5-line programs. They're not very interesting. Here we go. It's going to take a bit longer to compile the compiler and then record it, but it's not very long. And we are here, and this is the main function of the Go compiler. It's pretty short. We can step through it just like we did with the toy program. Just to prove that it's actually recorded, I'm going to set a breakpoint over here and type rewind, and it goes back. So it's recorded. But the interesting thing here is, of course, this gc.main. So let's walk all the way to this gc.main, and then we'll just step into it. And this is gc.main, where it's quite a long function. And this is where everything that the compiler does happens, essentially. And we could, sit here and step through this for the next 20 years. But we're not going to do that, because I don't have 20 years of time. So I'm going to show you one specific place that I think it's interesting from the point of view, doing a demo of a debugger. So we are going to go over here. Let's see if I can find it. Phase 5, 6, 7, yeah. 7, 8. This. I like this part personally. It's my favorite part of the compiler. There we go. We are here. So now, once we are here, the compiler has done its parsing, a bunch of type checking, optimization of the abstract syntax tree, which we don't care about today. And as you can see, this part here, it's a loop over this xtop variable. And then for each element of this xtop variable, it's called this function that it's called funccompile, which is, a potentially interesting name. So maybe we take a look at what's inside the xtop variable, right? So we could be tempted to simply look inside the variables window, but it's not there. And the reason it's not there is because the variables windows, as I told you before, simply lists local variables by default, but xtop happens to not be a local variable, it's a global. I know, shocking. And but that's not a problem for us because we can add stuff to the variables windows which is not local variables. To do that, we use the display command. And then we add, after display, whatever expression we want to add to the variables window. So in this case, just xtop. We can also shorten this command to dp, which is what I usually do. And there we go, and that's xtop. Now, let's resize this a bit. So once this thing is here, what we can do is we can change it. So this is an expression. So if we wanted to only see the first element of this xtop array, we could do xtop 0. And if we changed it, and it would be just the first element. Or we could also remove it if we don't care about it anymore. But we do for now. So I've looked around the compiler before, and I can tell you that what this xtop variable is, it contains the abstract syntax tree of every function that you are compiling, that is in your source code. And for example, if you wanted to find out this, let's say the index 1, if you want to find out, which function this represents, what you have to do is you have to open it, and then you have to go to the func member, and then you have to go over down here to the member that's called the name, and then we are not done, sim, and here it is, name. And this is the exact list function. And there we go. So as you can see, that's kind of complicated. If you were trying to debug this thing, this is a very deep structure, and you care about a member that's very deep inside the structure. So it would be nice that if when we all collapsed all this thing, right, we are not done collapsing, now we're done collapsing. So instead of this stuff that it's not useful, if it showed the name of the function that it's represented by that GC node, and we can do that. We have to give Gdlv a special custom formatter for the gc.node type, so that the Gdlv knows how to tell us what the name of the function is. To do that, we click on it. We say custom format for type. And now over here, we can type a script to format that every variable of that gc.node type in whatever way we want. And what we are going to do is we are going to do func plus x. So the x variable happens to be, whatever Gdlv is trying to show you. And then we are going to func the name, sim name. Then we type OK. And now we can actually see which function each of those gc.node variables represents. Now let's say we are looking for the function swap up. Now this is at index 7, and it's very easy to see because this is only 14 functions. But let's say sometimes when you're debugging a program, you have slices with hundreds of thousands of elements or even millions, and it can be hard to actually look manually through every one of them to find out exactly the one that you want. So there is a command to do that in Gdlv. It's called the find array command, and you give it first thing an expression to search. Okay. I typed enter accidentally, sorry. And the second argument that you're going to give is a predicate that will return true for the element of the array that you're looking for. It's either an array or a slice, it's indifferent. And this predicate has to be in a scripting language that's called the Starlark, which is a dialect of Python. So it's lambda, next, x equals 0. Func, the name, same, equals, let's say we are looking for a swap up. And we are expecting this to return 7 because we saw that it's at index 7. So we execute, and there we go, and it's at index 7. Okay. Okay, I'm going to show you how much time do I have? 8 minutes? Okay, I'm going to show you a few more things. When I'm out of time, you tell me I'm out of time and I'll stop showing things, okay? So, the first thing I'm going to show you, we saw how to set breakpoints by clicking on a function on a line and clicking set breakpoint. But sometimes we want to just set a breakpoint on a random function. And to do that, you can use the break command and then type the name of the function that you want to set the breakpoint to. For example, let's say we care about this compile SSA function, just randomly. And you can also shorten this command to simply b. There we go, and it's created the breakpoint. And now if we continue the execution, we can get back to the compile SSA function. Now, up to this point, I didn't show you anything regarding Go routines, and that's sort of a selling point of Go. So let's take a look at which Go routines are currently running. So to do that, we have to open the Go routines window, and we do that with this command, win Go routines, and we click enter, and that's the Go routines window. Now we can dock it, for example, over here. We're kind of strapped for space, so we'll have to squeeze a bit. Okay, so this is the list of all Go routines that are running on the program. The first one, Go routine 1, is always the Go routine that run the main function. And then there is a bunch of Go routines that are runtime stuff. They're used as helpers for the garbage collector. We don't care. And then there's these 4 Go routines at the end. So first of all, let's get back to the main Go routine number 1, and let's see what that Go routine is doing. And let's see, it's over here. And this is another interesting function. Whoops. So it's called compile functions. And what this does is it takes each one of those AST, abstract syntax tree variables that we saw before, and it starts a few worker Go routines that you can see over here. It wouldn't do that if you didn't specify -c equals 4. And then it sends work on a channel, and the worker Go routines take out the work. And you can see and compile SSA on it. So if we go back down to the Go routine that hit the breakpoint, we can see that if we go back, it's here. It's a worker Go routine. So all of these are worker Go routines. And okay, let's remove the xstop variable because we don't care about it anymore. And if we go back to the compile SSA, we can see that the fn argument of compile SSA function is also getting formatted with the custom formatted that we specified before. And let's say we continue again. What we see is that each one of these workers is getting an AST variable from the main Go routine and starting work on it. And the final thing I'm going to show you, I think, is I'm going to go back to the main Go routine one last time. And as you can see, the channel that sends work to the workers is called C. And you can see it over here in the variables window. And we can take a peek inside the channel. And there is a whole bunch of stuff in there. But what's interesting is that this buff variable, this buff member, which if we open it, that's the contents of the channel. And all of those are also formatted. And this is what's inside the channel that's been sent by the main Go routine, but hasn't been extracted from the channel yet. And that's everything I wanted to show you. If there are questions, either about this stuff over here, the graphical user interface for Gdlv, or for Gdlv itself, I've been contributing to Gdlv since 2015, so I know a couple of things about it. Yeah, there.
What do you use for the GUI, and what platforms does Gdlv run on?
So it's after him. There's a girl over there in the middle. Okay. She was first. So I'm using a graphical toolkit that I ported from C that's called Nuclear, like spelled wrong, and that thing renders using Shiny, which works on Linux, Windows, and macOS, and possibly other X11 operating system, but I have no idea. Unfortunately, it's slightly unmaintained, Shiny, so I think there are some bugs on macOS. When you resize, sometimes it crashes, but other than that, it should work fine.
What are the future features of Gdlv?
Sorry?
What are the future features of Gdlv?
Future features?
Features. What are the future features? The next features.
Oh, okay. I think I'm going to do an actual release, with a version. And most of the work, I think, is going to be on Gdlv itself. We are adding features to Gdlv, and then this will pick them up. I don't know, from the point of view of the graphical user interface, I don't have many, unmet desires. I didn't also show you everything on this demo. It's just a small subset of the features that I liked. So yeah, that's that. In terms of Gdlv itself, we are trying to port it to more architectures. Currently, it just runs on AMD 64. We recently added FreeBSD as an operating system, because that has, Gdlv has both problems. And ARM64 is probably going to be next thing. We are going to add better support for inline functions and better function call injection. That's one thing that we want to do.
Any other question? I do have a question, sorry. I went first. You showed us before that if you exit and enter back Gdlv, the breakpoints are saved and they are restored. Where are they saved? Is there a special file or directory?
In the configuration file. Oh yeah, see, I forgot to show you something before. If you remember this find array function that I showed you before, so the cool thing about that command is that it's not a built-in command. It happens to be also implemented using a scripting language. So if you go inside and look at less config gdlv.star, this is a starlark file that gets executed every time you start gdlv. And over here, that's where find array is defined. And as you can see, it has two arguments. The first one is the array expression, and the second one is the predicate. And what it does, it evaluates the array expression, and then loops through each element of the array and evaluates the predicate. And then it prints found I and returns the first time the predicate is true. And over here, there's also this configuration file, which is automatically maintained by the Gdlv from the user interface, and that's where the breakpoints are saved also. Yes.
The question maybe is more about Delv than Gdlv. Can you modify the code at runtime, either in assembly or maybe by rewriting?
No. So I've been thinking about doing that. That would be hot fixing, right, or patching, whatever exactly you want to call it. I think macOS calls it edit and continue. And yeah, I do plan to eventually do it. We need support for that in the linker and runtime. We can't just do that because the runtime needs to know that, you know, if you add a bunch of stuff to the memory of the target program, the runtime needs to be aware of what the hell this stuff is.
Thank you.
Other?
Thank you for the talk. I'm just curious, is the scripting capabilities you demoed here, are they part of Gdlv or are they part of Delv proper?
Which thing is?
The scripting, the star.
So it's client side, so what you're seeing here is part of Gdlv, but Delv has a very similar thing. So it's actually identical, it's the same code.
Cool, thank you.
So you can script Delv also in the same way. Anyone else? If nobody else has questions, then I guess we are done. So thank you. Thank you.